In question 3a part 1 we need to state the relationship between gravitational potential energy and the gravitational potential for a body of mass m placed in a gravitational field. Well, gravitational potential is the energy per unit mass at that point, and so the potential energy is equal to the mass multiplied by the gravitational potential. In part 2 we need to state the effect of doubling the mass on the value of potential energy. Well, the potential energy will be doubled if the mass is doubled. We then need to state the effect on the value of potential. Well, potential is a property of that region in space, regardless as to whether there is a mass present or not, and so the potential is unchanged. In B we're shown two orbits, A with a gravitational potential of minus 12 megajoules per kilogram, and B with a gravitational potential of minus 36 megajoules per kilogram. In B part 1 we need to calculate the radius from the centre of the Earth of orbit A. Well, gravitational potential is given by minus the gravitational constant times the mass of the planet divided by the distance from the centre of mass. We can rearrange this to give the radius or distance of the orbit from the centre of mass as this expression. The gravitational constant is on the formula sheet, as is the mass of the Earth, and this is the gravitational potential from the question, giving a distance of 3.3 times 10 to the 7 metres. In B part 2 we need to show that the radius of orbit B is around 1.1 times 10 to the 4 kilometres. Well, we can use the same expression as here, and the only thing that changes is the gravitational potential for orbit B, giving a height of 1.1 times 10 to the 7 metres, and there are 1,000 metres in a kilometre, and so this is 1.1 times 10 to the 4 kilometres as required. In part 3 we need to find the centripetal acceleration of a satellite in orbit B. Well, the centripetal acceleration will be the same as the acceleration due to gravity at this point, so we can use this expression, putting in the values, orbit B being 1.1 times 10 to the 7 metres, gives a value of minus 3.2 metres per second squared. The minus sign just gives the direction, which is obviously towards the Earth. In part 4 we need to show that the gravitational potential energy of a 330 kilogram satellite drops by about 8 gigajoules when moving from orbit A to orbit B. Well, the potential energy is given by the mass times the gravitational potential, as we showed up here, and so the potential energy at A minus the potential energy at B is given by the mass times the potential at A minus the potential at B, which is 330 kilograms mass of the satellite. This was the potential at A minus the potential at B, gives us 7.9 times 10 to the 9 joules, which is around 8 gigajoules is required. In part C we need to explain why we can't use the equation change in potential energy equals mass times gravitational field strength times change in height when finding the changing gravitational potential energy of the satellite in moving between the orbits. Well, the equation assumes a constant gravitational field strength, which is not correct over this huge change in height.